Greetings of the day. This is Abhishek Naluri. Welcome to my YouTube channel MSc Funda. Today we'll be learning something interesting. Strengthening mechanisms. And before we deal with the strengthening mechanisms, we have to understand the property of a material called strength. For suppose, given any material, you have a material with you or a metal. Being specific, it's metal. If you have a metal block or a metal element with you, and if you want to increase the strength of it, how and what way do you achieve it? And there are few mechanisms by which you can actually increase the strength of a material. And here are a list of 4 different mechanisms by which we can actually improve strength. And before we get into the main concept of strengthening mechanisms, we have to understand the basic term strength and what gives that property to the material. Strength is the ability of the material to withstand load without deformation, without plastic deformation. And what actually do I mean by plastic deformation? Getting into the atomic or the microscopic level, you'll understand plastic deformation, it is due to the movement of dislocations, and dislocation is nothing but a defect or an imperfection present within the system or present in the crystal. So if you have the movement of dislocation or that imperfection which moves, that results in the plastic deformation. So getting into the fundamental rules, so if you want to increase the strength of material, you have to impede or stop the motion of the dislocation. So once we achieve it, once we impede the motion of dislocation, we will increase the strength of material. So by using this fundamental principle, we will actually deal with these 4 techniques. And first, let us start with the grain size reduction. So you have a material and metal, and you have many grains. So in a metal, if you get into the cross-sectional view in a microscope, you'll actually see there are many grains. And these grains, as the size of the grain increases, what I mean is the size of the grain increases, the boundary area, the surface or the grain boundary area reduces. And as the size decreases, the grain boundary area increases per centimeter square of area, per unit area. So whatever the area, whatever the grain boundary or the total grain boundary what we are discussing, it is all related to per unit area or per unit volume. So as the grain size reduces, this boundary wall increases, and this boundary wall are something like the grain boundaries are something like the walls which are actually impeding this motion of dislocation. So that is how the enhancement of strength takes place, by when you reduce the size of the grain. And this is famously and well known by this Halpathy equation, sigma y equal to sigma naught plus k by root d, and where d in this equation, the d represents grain size. And since it's in the denominator, so smaller the value of d, the higher the value of the fractional value, and which actually increases the yield strength of the material. So that is how we can actually improve the strength of a material. And second mechanism by which you can achieve it, it's by solid solution strengthening. And during solid solution strengthening, we actually dope an alloying element or a foreign element atom into the matrix of the base or the parent metal. So if I have pure alloy, a pure metal, and if I want to add some alloying element or some impurity into the matrix of the original system, into the crystal, into the lattice of the system. So since there are 2 such scenarios where we actually dope it, and since doping is done with a foreign element or a foreign atom, the atomic size mismatches. The atomic size in comparison to that of the original base metal atom will vary. So it could be greater than, or the atomic size could be larger than the original atom, or it could be smaller than that of the original atom. And even at these such scenarios will generate stress in the lattice, and this stress will actually impede the motion of the dislocation. And here in these diagrams, it can be an interstitial solid solution, or it can be a substitutional solid solution. Interstitial, it's when we have this alloying or the doping element into the lattice, into the free space in the cell. And in substitutional, we are actually substituting a parent or a base atom with that of a foreign atom. So in such scenarios, in substitutional, for example here, assume this to be a substitutional solid solution. Here, if the atomic size is smaller than that of the base metal, and here the atomic size is larger than that of the base metal. So if it's smaller, this is how the stress fields look like, appears to be. Here it undergoes tension, and here it is